Alright, good morning everyone. Thanks a lot to attend my final defense. In this talk, I'm going to present you some of my rethinking of the foundations in GIScience, and I specifically focus on doing so from a higher order perspective. All scientific disciplines are built on some foundations. It is like building a house. Whether it is built on sands or rocks determines how far a discipline can go, and it is often worth the effort to check the foundation once a while to make sure it is still solid enough to hold the new add-ons. This is also true for GIScience. The development of spatial methods and techniques, as well as the addressing of real-world geospatial applications, all rest on the foundation of GIScience, such as the conceptual models of geographic information, Tobler's first law of geography, qualitative spatial reasoning, and so on. But why do we have to rethink the foundations, particularly at this time, and why from a higher order perspective? To answer these questions, I would like to start from a personal story. Inspired by the multiple point geostatistics, my very first paper at UCSB was on the topic of conceptualizing high-order spatial interactions in GIScience, which generalizes Professor Michael Goodchild's geo-dipole. Not long after it was published, I remember that one day Michael visited UCSB and stopped at the STKO lab, and we started talking about that paper. Then Waddle stopped into my office and joined us. They told me that they too had discussed about the similar topic dozens ago, but had not moved forward since then. After listening to what I have done in my first chapter, they encouraged me to further investigate two foundational questions that they have not figured out by then. Where and how does high-order spatial interaction matter in geography? And more importantly, in what ways would the new conceptualization change spatial thinking? GIScience is not only about the observation of geographic world, but also heavily rely on the development of information science and technologies. We believe that with the emergence of a new revolutionary information age, it might be the right time to bring the higher order perspective into the foundation of GIScience, which is out of the window 30 years ago. It is that inspiring discussion that motivated my further investigation on leveraging a higher order perspective to rethink the foundations in GIScience. In this talk, I share some of my findings and hope that they can address the two questions at least to some degree. First, you may ask, what is high order? In fact, this notion is originated from the three-body problem in physics, and it was first defined by Newton in his legendary book, Principia. The three-body problem is defined as the movement of three mass bodies under their mutual gravitational attractions, like the interaction between the Earth, the Sun, and the Moon. The higher order interaction has also been studied in disciplines such as neuroscience, biology, criminology, and social science, and they are doing so to understand the complex system of interest. In terms of high order spatial interactions, we define it as the spatial relations or interactions that involve more than two geospatial features in a broad sense. And more strictly, geospatial features have to be simultaneously involved in the relation. Namely, it cannot be decomposed into a set of pairs. For example, computing the directional angle requires at least 3 points, so it is a high-order measurement here. Specifically, 3 foundational principles and concepts will be discussed in this talk. They are pairs, topology, and Tobler's first law of geography. They correspond to 3 research questions here. Beyond pairs, ternary projective relations and direction are the first-class citizen. All are from a high-order perspective, and the first research question will be a conceptual base for the other two. And both research question 2 and 3 are related to directional information, one qualitatively and another one quantitatively. Alright, then let me directly delve into the first research question, which is asking, are there relevant geospatial patterns that cannot be sufficiently analyzed by using two-point association measures? To answer this question, let's first take a look at some classic approaches to measure geospatial pattern. No matter it is to quantify point pattern, spatial area pattern, field, or networks, we basically have two types of spatial measures. For the first order, or we call it environmental effect, its statistics is to check whether there is a constant mean across the domain. For the second order, or we call it interaction effect, we ask whether there are spatial associations or autocorrelations at different locations. Examples of spatial associations include the single distance class measure, such as the Morris I, and the multiple distance class measure, such as the semivariogram. As can be seen here, both are two-point statistics, as they quantify the attribute interaction between two locations, zi and zg here, and zxi plus h and zxi here. We also have local versions of these measures, such as Lisa and local Morris I. Nevertheless, all these are based on the pair comparison. Meanwhile, we have also seen the multiple point geostatistics being developed for the past decades, especially in the field of geology. The multiple point geostatistics aim to measure the spatial association that simultaneously involve attribute values at more than two locations. The general idea is that the high-order spatial association can be inferred from a training image rather than a fitted model like the semivariogram, and the templates, which is a higher-order neighborhood specification, can be used to scan the image in order to obtain the higher-order probability of data events. By leveraging this new statistic, we then ask whether the two-point spatial association is sufficient to capture urban structures that show complex patterns. To do so, we extracted 5 types of urban patterns from remotely sensed images and converted them to binary geographic fields where only the key geospatial patterns are preserved. And then we applied both two-point and multiple-point geostatistic to simulate them. As can be seen here, by using the semivariogram-based simulation, we can hardly distinguish the two produced pattern for pattern 1 and pattern 4. By comparing with their original fields, which are shown on the top row here, these two simulations demonstrate quite different structures. In contrast, after using the multiple point-based simulation, the two reproduced patterns clearly show different structures. The simulated pattern 1 are similar to the original pattern 1, where there are curvilinear structures like streams, while the simulated pattern 4 is similar to the original pattern 4 with polygonal geometries reproduced across the field. Here, we only demonstrate two patterns. The other patterns show similar observations as well. In summary, we observe that in terms of urban structures, there are cases where multiple point geostatistic could better capture geospatial patterns that are visually different with respect to the two-point statistics, such as variograms used here. To lift it into a conceptual level, we then explore how to extend the traditional low-order interaction model to its higher-order version. Concretely, we follow Goodchild's geo-dipole and generalize it into a new conceptualization called geo-multipole, where the interaction between two locations x and x prime is replaced by the higher order interaction of x and its collective neighbor Tn. This neighborhood Tn can contain more than one locations. Capitalized Z here indicates the type of the interaction, and the lowercase z here represents the interaction value. So what do we gain by generalizing the geo-dipole to the geo-multipole? In fact, interactions in geo-dipole are considered in pairs despite that multiple pairwise interactions can be combined. While for geo-multipole, the n locations are simultaneously considered when modeling their interaction with the target location x. Namely, the geo-dipole can only model the higher order interactions in its broad definition, while geo-multipole focuses on its strict definition, where the interaction or relation cannot be decomposed into a simple combination of pairs. For example, the statement A is between B and C has to be modeled using the geo-multipole rather than the geo-dipole because it cannot be composed into pairs such as A is between B and A is between C. In summary, in this research question 1, I empirically motivated the account of high-order spatial interactions in spatial analysis. I also proposed the geo-multipole, which is an extension of the geo-dipole, to conceptualize high-order spatial interactions. I also methodologically discussed the statistical models like the multiple point geostatistics to study the higher-order spatial interactions. Using the geo-multipole as a conceptual base, in research question 2, I seek to answer how to represent and reason over high-order qualitative geographic information in geospatial knowledge graphs. Here, I specifically focus on qualitative spatial relations. Based on their cardinalities, qualitative spatial relations can be categorized into mainly 3 groups. The binary relations are the most commonly studied ones in GIScience. It includes the topological relations such as contain, touch, overlap, and so on. Here we can see 3 objects overlap with each other. It sounds like a high order, as it involves 3 entities, but overlap itself is still fundamentally binary because we can decompose the relation into 3 overlaps. Next is the ternary relations, and the projective relation is a classic example, which includes between, left, right, before, and after, as shown in this figure here. In addition, we also have n-array relations, where n is usually larger than 3, and surroundedness is a good example. In this talk, I focus on ternary projective relations and leverage knowledge graph to represent and reason over it. Knowledge graphs have been studied for representing binary spatial relations in the form of subject, predicate, and object. One example is like A overlaps B. In order to use the same framework to represent the ternary relations, here we use the concept reification. Specifically, we construct a new class for each ternary relation. By doing so, the relation class can have multiple property edge representing the different roles of each involved entities or places here. As a result, we proposed 2 ontology design patterns. The first is to model the relation of left, right, before, and after. in which the highest target edge links to the place to be located, has origin and has destination jointly define the frame of reference. In terms of between, we design another pattern for it as it has the symmetric property. In this pattern, the has origin and has destination are both replaced to has reference here. Here is an example of a knowledge graph based on ternary projective relations. We have 5 cities, and 3 relations statements are represented as Southern Oaks is between Los Angeles and Ventura. Santa Barbara is before the route from Ventura to Los Angeles, and Fillmore is on the left from Santa Barbara to Southern Oaks. After knowing how to represent it in knowledge graphs, we next explore how to reason over it. As I have just showed, one relation statement can in fact be represented as a tuple of 3 row-value pairs, as shown in this example here. Fillmore is the target of the left relation, Santa Barbara is the origin, and Southern Oaks has the row of destination. Based on this representation, we further define 2 tasks. Firstly, spatial relation prediction aims to predict the missing rows given 3 observed places. A corresponding question can be, what is the spatial relation between Santa Barbara, Ventura, and Los Angeles? Secondly, place prediction attempts to predict the target place given the relation and the other 2 places. In natural language, we can ask which city is on the left side from Santa Barbara to Southern Oaks. To accomplish these 2 tasks, we designed a neural network architecture in which we regard each row and value as a high-dimensional embedding vector, as shown for example here. The row of between target is represented as a k-dimensional vector with each dimension being represented as a numeric value. We do the same for the value Ventura. We then concatenate them into a 2k dimension row value pair embedding, and we do the same for the other 2 row value pairs. Using the embedding, we then compute the pairwise relatedness score of the 3 row value pairs in a relation. For example, the relatedness of between target Ventura and between origin Santa Barbara will be computed here, and the same for all other possible pairwise combinations. With this pairwise relatedness score, we further compute their overall compatibility score for this relation statement. The intuition underlying this model is that the more related of the 3 row value pairs in a relation statement, the higher the compatibility score will be, and then the more likely this relation statement to be true. The embedding of rows and values are learned by training the model, and the training process aims to minimize this logistic loss function, where I here equals 1 if the statement is true, otherwise it is -1. S here is the compatibility score we have just discussed. We need both positive and negative samples to train this model. And the positives are our training data. Then we have to use the negative sampling technique to generate negatives. Here, we randomly replace the row and the values in a positive statement to some other rows and values so as to generate negative candidates. Finally, we used the atom as a stochastic optimization method for backpropagation. Even though this model can predict general higher-order relations, it is not spatially explicit. For ternary projective relations particularly, we observe that it has three characteristics, including the strict definition of higher order, mutual exclusivity, as well as their conceptual neighborhoods. I will discuss them one by one and show how we modify the model to make it spatially explicit. First, ternary projective relations are strictly high order. To explain it, let's first see a general high order relation. Marie Curie received the Nobel Prize in Physics in 1903 together with Henry and Pierre. If we decompose it into binary relations, such as Marie Curie received the Nobel Prize in Physics, it is still valid. On the contrary, a ternary projective relation such as Ventura is between Los Angeles and Santa Barbara cannot be decomposed into pairs. For example, the statement of Ventura is between Los Angeles is semantically invalid. To take this high-order relatedness into account, we replaced the pairwise related computation as shown here with a ternary one as shown here. In this architecture, the relatedness between these three row value pairs are simultaneously considered. Secondly, the five relations of ternary projective relations are also mutually exclusive. For instance, if we know Fillmore is on the left from Santa Barbara to Thousand Oaks, then the relation statement like Fillmore is on the right of Santa Barbara to Thousand Oaks becomes false. Based on this domain knowledge, we replaced the random negative sampling strategy with a mutual exclusivity induced one, which is shown in this formula here formally. Similarly, ternary projective relations have their conceptual neighborhoods. The notion of conceptual neighborhood was introduced to describe the direct, discrete transition between temporal and spatial relations. Here, for ternary projective relations, we have their conceptual neighborhood listed in this table. Like the mutual exclusivity, we design a new negative sampling strategy using this domain knowledge. The intuition behind it is that a relation is easier to be confused by its conceptual neighbors, so more difficult negative samples generated according to conceptual neighborhood would help improve the model's performance. For example, the statement Fillmore is on the right from Santa Barbara to Thousand Oaks can generate negatives using the relation between, before, and after as they are neighbors to the relation right. However, the relation left will not be sampled here because it is not the neighbor of right based on this table. To evaluate the method, we built a knowledge graph of ternary relations. It composes 764 significant cities in the 4 western states of the U.S., California, Arizona, Nevada, and Oregon. These data were collected from DBpedia places. In total, we sampled about 40,000 relations and split them into 80, 10, and 10% for training, validation, and testing, respectively. We used different metrics to evaluate the two tasks, which are consistent with the literature. And here is a table showing the experiment results of multiple combinations of the proposed methods. In general, we have two conclusions here. First, we found that leveraging the 3 types of geospatial inductive bias can indeed improve the model's performance. Second, the model, which combines the high-order relatedness with the mutual exclusivity-induced negative sampling, achieves the best result, which is about 20% higher than the baseline. This is shown in red line here. In summary, to answer this research question too, I proposed a way to represent the ternary projective relations in geospatial knowledge graphs. I designed a neural network architecture to two spatial reasoning tasks and their spatial relation prediction and place prediction respectively. I also accounted for the characteristics of ternary projective relations to make the resulting model spatially explicit, and these biases include the higher order relatedness, mutual exclusivity, as well as the conceptual neighborhoods. If you say my research question 2 is more about qualitative directional information, my research question 3 will more focus on quantitative directional information. Specifically, the question is framed as, do the development of early GIS, data sparsity, and Tobler's first law of geography lead to a theory-induced blindness for the role of direction? If so, is it possible to envision direction becoming a first-class citizen of equal importance to distance? I believe all of us here already know very well of Tobler's first law of geography, which states that everything is related to everything else, but near things are more related than distant things. In fact, this law is the backbone of many spatial methods. We widely regard it as the law of spatial dependency. However, when we quantitatively measure spatial relations between locations, there are two essential components: distance and direction. However, the first law only focuses on distance, as the word near and distant indicated here. Therefore, this law implicitly has an isotropicity assumption, and by isotropicity here, I mean the invariance to rotations. Put differently, this law assumes the directional variation is negligible, but is it really an appropriate assumption? That's our question. Here, we believe that anisotropicity is the norm rather than an exception. As shown here, our geographic space, like the terrain model, is often anisotropic, and the geospatial processes, like the smoke propagation of atmosphere, are also anisotropic. Then, the geospatial patterns, which are the observations of the geospatial processes working on the geospatial space, are more likely to be anisotropic as well. Even though directional effect, or anisotropicity here, plays an important role in many geospatial applications, typical GIS does not provide many options for us to deal with that. For example, to estimate the location of an offender in a crime, we would like to draw an anisotropic buffer with the long axis along streets, like the green buffer shown here. But the GIS typically only provides an isotropic buffering operation, like this pink buffer. Similarly, for our mostly used spatial autocorrelation measures, such as the Marin's Eye, Gear's C, and LISA, the weight WIG only captures pairwise distance and adjacency information. Direction is often regarded as an afterthought, only considered when the deviation from a perfect circle becomes too obvious to be ignored. While the causes behind the isotropicity assumption is uncertain, possibilities include these three facts. First, direction is hard to be computed. Unlike the ordinal or interval scales, direction is measured based on a cyclical ratio scale, which is more challenging to process. Second, since directional information is higher order, it is computationally demanding, as statistics based on it require a larger number of samples. Thirdly, we speculate that there is a theory-induced blindness, like the Tobler's first law, that lead us to understate directional effects and think that distance is capable of capturing directional information. But is it really the case? Let's take one of the very current work on similarity measures of flows as an example here. In this paper, the authors proposed to use the distance between origins and destinations as well as the length of the flows to compute the two flows' similarity. They explicitly mentioned in their paper that these four distances implicitly capture the directional information of the flows. However, we found that this measure can hardly tell the difference between the three pairs of flows shown here. Obviously, directions of these flows play roles to distinguish them. As can be seen, the first pair, they are parallel. The second pair, they cross with each other. And the third pair, they origin from the same point, but diverge into different directions. In addition, there are in fact two types of isotropicity. One is the radial isotropicity, where a global origin is applied, and another is the stationary isotropicity, where the origin is defined locally. In fact, these two describe very different and complementary directional information. For example, by considering the radial or global isotropicity, flow C here will be more similar to flow E and F compared to flow D. But when using stationary isotropicity, flow C is more similar to D than E and F. By studying the literature, we found that many research only consider the stationary case in their model, while the radial isotropicity is still very helpful to study the flow patterns as well. For example, when studying the global migration flow, by considering this stationary isotropicity, we can group together flows that are from southern hemisphere to northern, such as the flows from Mexico to US and North Africa to Europe, even though the origins and the destinations of these two flows are thousands of kilometers apart. To further explore the role of direction in spatial analysis, we conducted a series of thought experiments here, in which we developed several distance-free statistical methods, including pair variance, angular variogram, cosine angular weighting, as well as the directional association. In this talk, I will only focus on the cosine angular weighting. Moreover, it is worth noting that the ultimate goal here is to inspire alternative thinking on modeling geographic information, with an emphasis on the role direction could play as a first-class citizen in GIScience. It does not imply that direction-only techniques should replace those that are based on distance. Here, imagine we observed the smoke level at 4 locations, S1, S2, S3, and S4. We want to use them to estimate the smoke at the unknown location S0. By using inverse distance weighting, since S3 is closer to S0 than S2 to S0, S3 will have a larger weight in the model. In contrast, if we consider directional effect, that the smoke is from the northeast to southwest, We then can assign a larger weight to S2 than to S3, as the direction from S2 to S0 is closer to the smoke propagation direction. Therefore, compared to the inverse distance weighting, the cosine angular weighting approach achieves a more accurate estimation to the true value at S0. To address the theory-induced blindness, we therefore propose to generalize Tobler's first law into a collinear version where both distance and direction are taken into account. It is stated as everything is related to everything else, but near things and those that point in similar directions are more related than distant things and those pointing in different directions. We hope this simple law can keep guiding researchers to develop new spatial methods in GIS, but with directional effects in mind as well. In summary, by answering question 3, we found that variance increases with distance, but also with direction. Anisotropicity is a norm, not an exception. Although anisotropic techniques exist in GIS and GIScience, they remain to be an afterthought. New techniques or GIS notions can be introduced here purely based on direction. The generalized Tobler's first law highlights the role of both distance and direction in spatial analysis. In conclusion, in this talk, I showed that higher-order spatial interactions benefit of our understanding of complex urban structures. The geo-multipole provides a new conceptualization for studying spatial interactions. An intelligent agent can be trained to reason about high-order qualitative spatial relations without using geometry. Geospatial domain knowledge indeed contributes to the performance. Last but not the least, anisotropicity is a norm rather than an exception in geospatial processes. The generalized Tobler's first law of geography raises the role of directional effect in spatial analysis. In terms of the outlook, I would like to explore other downstream geospatial applications under the framework of the geo-multipole. I would also like to investigate the potential of leveraging new data models to represent and reason about higher-order spatial relations, and I'm particularly interested in the spatial complex here. And I would also like to promote the directional effects in GIS education and spatial thinking more broadly. Finally, I would like to study the temporal aspect of higher-order interactions. Finally, I would like to conclude my talk by acknowledging my committee members, Jano, Fierden, and Keith, for their advice and supports. I would also like to thank Kostas, Helen, and Werner for their time discussing with me and addressing my research concerns. I'm lucky that my research has been funded by multiple parties, including NSF, Siemens, Esri, and iOS Press. I should thank these organizations. Last but not least, I'm very proud to be a member of the STKO lab, and I appreciate all previous and current STKO members' help on my research and life. I show two pictures here. On the left, you see how happy we were in the lab, especially when each of us had a cup of coffee holding in hands. And on the right, you see how we meet in Zoom and how much we hope to get back to the campus. Thanks a lot for your attention, and I'm happy to answer any questions.